Good morning, everyone. My name is Vinay Mutani, and along with my team members Vaibhav Pandya and Sanskriti Sharma, we will be presenting on a topic that sits at the intersection of biometrics and deep learning. Our topic is super resolution of fingerprint using ESPCN. Fingerprints have been one of the most trusted forms of biometric identification, but in real world situations like low quality sensors, partial prints, or noisy data, the fingerprints we capture often lack the resolution needed for accurate recognition. That's where super resolution comes in. In this presentation, I will walk you through what super resolution is, how ESPCN works, and why it is particularly effective for fingerprint enhancement. We will also take a look at some results and discuss this technology that can make real world impacts in areas like forensics, security, and digital identity verification. Our problem statement is in forensic investigations, fingerprint evidence plays a vital role in identifying individuals and linking them to crime scenes. However, fingerprints collected from such environments are often of low quality issues due to smudging, partial impressions, environmental conditions, or poor acquisition devices. These low resolution images can lack fine rich details and minutia required for reliable matching and identification. Conventional image enhancement techniques such as bicubic interpolation often fails to reconstruct the necessary texture and clarity, resulting in blurred or distorted ridge structures. This limits their effectiveness in forensic context where accuracy is critical. Therefore, there is a pressing need for an advanced, efficient method to enhance the fingerprint resolution, enabling better clarity, improved feature extraction, and higher confidence in forensic fingerprint matching.
Now, talking upon the methodology, we have used the concepts of ESPCN algorithm, which is efficient subpixel convolutional neural network, which is designed to perform a single image super resolution by reconstructing a high resolution images from the low resolution input. Now, unlike the traditional methods, it upscales the images before pre-processing them. Now, ESPCN directly operates on LR images, enhancing their efficiency and performance. Now, here we can see that initially we have used the data set which is NIST4, which in which we have inputted the same and done the pre-processing, which includes steps like normalization and augmentation of the low resolution images, followed by training and testing the pre-processed image on the ESPCN model. So using the LR-HR pair to train the model. Now finally, we have done the ESPCN evaluation on the concept on the evaluation matrix that is PSNR. Now I will be showing you the project demonstration, like the coding part. So this is the entire project repository, and we'll be running the same. So I have run the train.py file, and this is the final results that we can see on the screen. Now it includes majorly 5 images. The first is HR image, that is high resolution, followed by bicubic image, and SR is here stands for super resolution image, and the fourth is LR image, which is low resolution image. Now here we can see that the final evaluation matrix that we have got is 29.23. So we can conclude that our model is comparatively good than bicubic. Now moving further, hand over to Vinay.
This is our dataset we took from Kaggle. Now, my friend Vaibhav will explain you about the result of this research.
So as you can see in the result, we have got about 4 images. First one is high resolution image. We have given the low resolution image, which is in the right of the image, which is given in the form of LR image. And then we have bicubic image, which is the traditional form where deep learning is not used. And third one is super resolution image, where we have used deep learning. In non-traditional method, that is bicubic interpolation uses the weighted average of 16 neighboring pixels, a 4 into 4 grid, to calculate the value of a new pixel. It is a deterministic algorithm, no training or learning involved, smooths out the image and tries to maintain edges between the bilinear or nearest neighbor interpolation. The pros of this method is it is simple and efficient, no need for training data, built into most editing tools and libraries, can introduce, but the cons in this method is can introduce blur, not great at recovering fine details, limited performance and high upscaling vectors. While we are using ESPCN for the third image, that is super resolution image, we have used deep learning CNN for this. It trains a CNN to learn the mapping between low resolution and high resolution images, uses a clear sub-pixel convolution layer to the network, which is more efficient and avoids early upscaling that can slow down processing. Learns texture and structures from data, so it can reconstruct sharper, more detailed images. Better visualization quality and detailed restoration are its pros, and efficient and real-time capable. And it's especially good for video super resolution. Cons. The cons of this method is requires training with high quality image datasets heavier than transitional methods. Performance depends on quality and variety of training data. And we as you can see on the output, our peak signal to noise ratio comes about 29.23, which is an good thing, and the highest it can go about 40, which is an excellent. We have trained about 500 images. We have trained this data on 500 images, so our PSNR comes about 29.23. Now Sanskriti will move over to next slide. Thank you everyone.